A course in paleomagnetism. Hi and welcome to GeoCave. I'm Asha, I'm a geologist living in Norway. On this channel I talk about anything geology related. And today we follow up with a video on our course in paleomagnetism. If you want to watch only one video in this series, this should be the one. It's the big kahuna of paleomagnetism. So grab a cup of your favorite drink and let's see what's in the cave today. In ferromagnetic materials, atoms align in regions called magnetic domains. Small magnetic particles have their magnetic spin perfectly aligned, making them uniformly magnetized. These are called single domain particles. Some particles, although not perfectly uniform, still share many properties with single domain particles. These are called pseudo single domains. When particles grow even larger, they split into multiple magnetic domains. These domains are separated by areas where the magnetic direction changes rapidly. The next one we're going to talk about is the hysteresis curve. Hysteresis refers to the phenomenon where a state of a system depends on its history. Hysteresis curve is created if you put a sample of a rock in a machine and then the machine flips the magnetic field back and forth. You get a diagram like this. The y-axis shows the magnetic flux density of the sample, and the x-axis is the surrounding magnetic field. P shows the magnetic saturation. Hysteresis curve is mostly used to decide the domain of grains in the sample. The shape of the graph tells you which kind of grain it is. When the surrounding magnetic field is 0, R shows the sample's remanent magnetic field. So now let's talk about one of the great scientists in paleomagnetism. The preservation of ancient magnetic fields is based on the work of Neel. This theory explains how magnetization decays over time. He investigated how single domain grains transformed into super-paramagnetic over time. Super-paramagnetism is when a mineral flips its magnetization. It happens to all magnetic minerals and depends on two factors: the relaxation time and the blocking temperature. The relaxation time is the average time it takes for the magnetization of a particle to flip direction due to thermal fluctuations. It is given by the Neel-Arrhenius equation, which I will put it up here. And the tau 0 is the characteristic attempt time. Big K is the anisotropy energy constant. V is the volume of the particle, and small k is the Boltzmann's constant, and T is the temperature. Blocking temperature is the temperature below which the magnetic moments of the particles are blocked and cannot easily flip direction. Above this temperature, thermal energy is sufficient to overcome the energy barrier. causing frequent flips in magnetization. The blocking temperature is defined by the condition where the relaxation time, tau, is comparable to the measurement time. Now we will talk about another concept in paleomagnetism, and we will start off discussing Curies temperature. The Curies temperature is the point where a material loses its permanent magnetic properties. Meaning, if you heat up a magnetic mineral up, it will at some point lose its magnetization. If you turn it around and a rock is newly formed and are very hot, the Curies temperature is when the rock is cool enough to preserve the magnetic field it's surrounded by. Every magnetic mineral has their own Curies temperature, so therefore we have something called the susceptibility curve. Magnetic susceptibility is a number telling how magnetic mineral respond to its surrounding magnetic field. In other words, how easily it gets magnetized. So the susceptibility curve combines these two, the Curies temperature and the susceptibility. It measures the susceptibility while heating a sample up. So when the sample reaches the Curies temperature, you see that all the magnetization disappears. And in that way you can tell which mineral you have. So, natural remanent magnetism. This is the permanent part that doesn't change and is important for studying the Earth's past magnetic field. Natural remanent magnetism is made up of primary natural remanent magnetism, formed when the rock was created, and secondary natural remanent magnetism, added later due to events like chemical changes or lightning strikes. Thermoremanent magnetism occurs when a magnetic mineral in rocks cool down from high temperature in the presence of a magnetic field, such as the Earth's magnetic field. So it's recorded mostly in igneous rocks. As igneous rocks cool from above the Curies temperature, the temperature at which a certain material loses their permanent magnetic properties, the magnetic minerals within them align with the Earth's magnetic field. Once the rock cools below the Curies temperature, these aligned magnetic minerals lock in the direction and the intensity of the Earth's magnetic field at that time. This form of magnetization is very stable and can last for millions of years. Chemical remanent magnetization happens when new magnetic minerals form or existing ones grow to chemical reactions like oxidation or crystal growth. During these changes, the minerals align with the Earth's magnetic field, recording its direction and intensity. Chemical remanent magnetization can modify or overprint primary magnetization. Detrital remanent magnetism is a type of magnetization that also occurs in sedimentary rocks. Detrital remanent magnetization forms when fine magnetic particles in sediments align with the Earth's magnetic field as they settle through water and become part of the sediment's layer. These particles, often smaller than 10 micrometers align with the geomagnetic field, recording its direction and the time of the position. Once the sediments are compacted and lithified into rocks, the magnetic alignment is preserved, providing a record of the Earth's past magnetic field. Detrital remanent magnetism is particularly useful for studying paleomagnetic record of marine and lake sediments, helping scientists understand historical changes in Earth's magnetic field. So that's it for today. I hope this was valuable for you and that you now have a deeper insights in paleomagnetism. But rest assured, this isn't the last chapter in this course. I will continue. I don't know if it will be next week, but let's see when I will have the time. But that's it. Thank you for watching so far. Have a rocky day. Of course.